Alrighty, so today we're going to continue on doing our fun equilibrium stuff that we started last week. This is a pretty short chapter for us. It's pretty much just going to be today. For the kind of the rest of the new material, and honestly, a lot of the stuff we're doing today is just practice anyway. And so I guess tomorrow we'll just do some more problems, and then Wednesday we'll just have our exam review. So you have your exam next week. I guess it's going to be Tuesday since I think Monday's a holiday. Maybe not. Check the syllabus. I'll check that as well. But your exam is next week somewhere in there. So we'll have our review thing. I'll try and find a practice exam to put on Canvas for you guys, so you can kind of see what sort of questions and that sort of thing that'll be asked. So you can be kind of prepared for that, and you can ask questions on some of those. I'll put an answer key as well, so you'll be able to see. Alrighty, but in the meantime, let's go ahead and just kind of start with a practice problem. Let's go ahead and say we have this reaction. Say all these are gases. All right, and let's say that Kc is 49.7. Let me actually move that somewhere else. 49.7. Okay, and let's say we start with 1 molar of hydrogen and 2 molar of our iodine. And let's go ahead and see what the concentrations are going to be at the end of, or once equilibrium is established. So we'll make our ice table as always. I guess I'll write the question out here. What is the equilibrium? I guess I have to change it to R, don't I, since we have more than one, of course. We're going to look at the equilibrium concentrations for all of these, and let's go ahead and say these are in units of molar, just so we have something out there. So let's go ahead and do that. Remember that we want to first double check our reaction is balanced, of course. Looks like it is, so we're good. We're going to be consuming our reactants. Since we do not have any product in here, we're going to see later today what to do if you do have some product already. How do you know to do minus X or plus X or what have you? We'll get through that later. All right, notice we have a 2 as a coefficient for the HI, so we're going to go ahead and throw 2x there. So we'll have 1 minus X, 2 minus X, and then 2x. If we go ahead and look at this equilibrium expression, we know that Kc is going to be Hi squared over H2 times I2. Concentrations of all those, I'm just ignoring the brackets for now. So that'll be 4x, or let's just put it this way, 2x squared. We have 1 minus x, 2 minus x, and this is going to equal to 49.7. How exciting. If we go ahead and do this algebraically, we have 4x squared. It's going to equal 49.7 times, let's see if I can do this in my head, 2 minus 2x plus x squared on the bottom. Hopefully I can do that sort of math in my head. No, apparently I can't, because it should be minus 3x. Right. We can go ahead and throw this in our calculator, or we can use our quadratic formula here. Technically, we should distribute those. So 4x squared equals, what is this going to be? 99.4 minus, oh, forget it. Why am I trying to do stuff in my head? 3 times 49.7. 149.1x plus 49.7x squared. Let's go ahead and just subtract 4x squared. So that'll bring this down to 45.7x squared. We can go ahead and throw in our quadratic formula now if we really wanted, or we use the unlimited power of the internet, which is what I'm going to do. Solve for x calculator. Alrighty, so let's see, we have 45.7x squared minus 149.1x plus 99.4 equals 0. Let's see what we get here. Hopefully some nice numbers for us. I hate when it does this. Why wouldn't it actually give me a number? It's giving me these horrible fractions to deal with. Let's see if this, okay, there we go. And doing this, we get two options here. We have 0.93411 or x equals 2.33. If we go ahead and look, is there any way that x could be either of these numbers? Yes, it looks like the first one is acceptable because we can have 1 minus 0.934. That's a totally valid number. However, we cannot do 1 minus 2.33. That's not an acceptable solution because that will give us a negative concentration, which is not allowed. So we're going to go ahead and say x is going to be this number. So our concentration of x, or hydrogen, was 1 minus this number, which is going to be 0.0. I can do this. 7 if we do the sig figs properly. Why is subtracting so hard? 0.93411. Let's just make sure. Yeah. If you round it, it should give 0.07. I2 will be 2 minus that number, which will be 1.07. And then, of course, the HI will just be, since remember it's 2x is going to be our concentration, we're going to have 2 times 0.93411, which is equal to 1. Let's see, 8. Oh, forget it. Never try to do math in your head. That's the answer here. 1.87, we'll say, molar. Hooray! We did it. Exciting stuff. So, much the same sort of thing we did before. Equilibrium stuff, you're always going to kind of deal with an ice table. It makes it nice when these x values are easy to work with. Quadratic equation should not be anything kind of scary for us. We know how to use the quadratic formula or to use Google. And so either one of those will work. So, cool. Alrighty. Any questions on that one? Alrighty. So let's look at how to predict which way an equilibrium is heading. So that means, is it currently going to favor the forward or reverse reactions? And so we're gonna, good morning. We're going to have another kind of term that we're going to use in order to evaluate this question, which is called the reaction quotient. This is Q. And Q is the same thing as your equilibrium expression. So if we have our same reaction from before, it's going to be the same as your equilibrium expression, with one kind of caveat there. Let's make that lowercase. You'll see it looks very much like Kc, right? Or Kp. Well, I guess these are concentrations because of the brackets, but Kc is for equilibrium concentrations. So it's the concentration at equilibrium, once you've already established equilibrium. Q can be done or evaluated at any time. So you can take a look at Q at the start of the reaction, after a few minutes, or at equilibrium. You can kind of take a look at it at any given time. And so we're going to be able to use Q as kind of seeing a snapshot of where our reaction is by comparing it to Kc. So we're going to see that if Q equals Kc, that means that the reaction is at equilibrium. Right? We would expect them to be the same. Excuse me. If Q is less than Kc, let's take a look at what that's going to mean. So if Kc is our kind of normal, equilibrium expression, if Q is going to be less than Kc, that means we have two options. Either we are going to have not enough reactants, or we have too many products, or both, perhaps. In that case, we're going to see that we're going to have the equilibrium, or the reaction rather. We're going to see that the reaction is going to be favoring the reactants. So if Q is too small, we have too many products or too few reactants compared to what they should be at equilibrium. And so we're going to see at the time of a Q being smaller than Kc, our reaction is going to be producing more products. Producing more reactants. That's what I meant to say. Sorry. It's just confusing, and all the freaking words are all the same. And of course, if Q is greater than Kc, it's going to be the opposite, right? So that means your reaction is going to be favoring the products. So your reaction is going to be working that way. So we're going to see how to use this Kc fun stuff, or rather Q stuff. So let's take a look at an example reaction and see how we can apply this. So our favorite Haber process from before, 2 ammonias, all these gases, of course, and at our particular temperature, our equilibrium constant is 5. So let's see what's going to happen. Let's say these are going to be our mole values here. If we put 1 mole, 3 mole, and 0.5 moles into our reaction vessel, and let's say the reaction vessel is 50 liters, let's go ahead and see where this reaction is in terms of like where it's headed, what's going to happen with it. So let's go ahead and do that. So if we go ahead, we have to use concentrations here. We can't use moles directly. So let's go ahead and just throw all these mole values into concentrations instead. If we do that, we get what's 1 over 50, 0.02. And then that would be 0.06 molar, and then 0.01 molar. All right. If we take a look at Q, same thing as kind of the way of structuring Kc. So we're going to say that it's going to be ammonia squared and then we have nitrogen and hydrogen at the bottom. If we do this, we get 0.01 squared, 0.02, 0.06 cubed. It's a really ugly cube. We'll fix that. Let's go ahead and do the math. 0.01 squared divided by 0.02 divided by 0.06 cubed. Hopefully we get something here. Yeah, I get 23.1, we'll say, if we do the math. So we can see that our Q is 23.1. Our K is 0.5. So we can see here that our Q is definitely greater than Kc, which means right now we have too many products, right? Our reaction is currently favoring the products. So as a result, what's going to happen is our reaction will kind of have to, we're going to be, as a result, getting rid of those extra products. So our reaction currently favors the products when it shouldn't. So we're going to say that what's going to happen now is that we're going to have to kind of use up this ammonia. So we have too many products going on. Our equilibrium is not happy. So if it wants to reach equilibrium, it's going to have to get rid of that extra ammonia. So instead of continuing to favor the products, it's going to have to go backwards and do the reverse reaction, get rid of some of that ammonia instead. All right, so how the equilibrium shifts is going to be the opposite of kind of where it's favored. So right now we're favoring the products. We have too many products. So our reaction will kind of shift itself such that we're going to end up using up those sorts of things. If we take a look at what this kind of means graphically speaking, let's say we have just some reaction, I don't know, A turns into B equilibrium-wise. If we take a look at A and B, let's go ahead and see what this might look like on a graph. That's really ugly, isn't it? Let me try that one again. There we go, kind of. So we can kind of look here. We've kind of got three areas of this graph. Right here in the middle, let's say these are concentration units, by the way. We don't really have an x-axis because this is not a reaction that's happening over time, but just kind of looking at this. So if your concentrations are going to be unchanging or relatively so, if your artistry skills are better than mine, kind of that middle section there is when, I guess I have to put the colors on these, don't I? Let's say that B is going to be blue. I guess we're doing the reverse reaction here, whatever. That's okay. And we're going to say that the black one is A. Okay, so if they're unchanging, that's when Q is equal to Kc, right? Your reaction quotient, what you're looking at your snapshot in time, is going to be equal to your equilibrium constant. If we look at either of the sides, though, we see here we have too many products. Products. If you have too many products, that's the same thing as saying Q is greater than Kc. And then we must say that the reaction must go in reverse. Because it's favoring the products, it's not allowed to do that, so gotta go backwards. If, on the other hand, you have too many reactants, that means your Q is going to be less than Kc, and that means reaction must go forward. So you can use this kind of evaluation of looking where Q is in relation to Kc to see which direction your reaction is going to go. You can see also where it is right now, and then as a result where it's going to go. So if it is currently favoring the products, that's not allowed. It's got to have to make more reactants. If it's currently favoring the reactants, we're going to have to make more products. So it's always kind of the opposite thing here. We have to reestablish our equilibrium. All right. So you can kind of just use this value of the reaction quotient to kind of just take a look at your reaction kind of in real time to see, what's happening with it. What are you going to see happening to that reaction? All right. Questions on that one? Or that topic, I guess. Alrighty. Let's just talk about Kc a little bit more, or Kp. We're going to see that much like when we saw that enthalpy could be, the dashed line area, if my artistry skills were great, those lines would be slope of 0, straight lines parallel to each other. That's where that would be at equilibrium, yeah. In that kind of area in between. So I'm sure there are much better graphics for this online or in a textbook or something, but my artistry sucks. I'm sorry. Anyways, so much like what we did with delta H and Hess's law. Remember, with Hess's law, we could take individual reactions and combine them together to make an overall reaction, and we would be able to combine their delta H's to get the overall delta H for the reaction. We're going to see that we can do this with equilibrium constants as well. So here we go. Here's a couple of reactions. All right, here's reaction 1, and here's reaction 2. Let's just say all are gases for right now. I just don't want to write them all out. So, if we were to combine these reactions, if we do that, we're going to see, okay, what's going to cancel out here? Methane will cancel. 3 of our hydrogens will cancel out. So, in fact, all of that one's going to go away. The rest of the stuff will all stay here. So our combined reaction overall will be the following. So just including everything that's still there after we cancel stuff out. If we're to look at the equilibrium expressions for these, for our reaction 1, that's going to be CH4 times H2O over carbon monoxide times hydrogen cubed. If we look at for reaction 2, CH4. And then our combined reaction, reaction 3. Put all these guys here. If we look at what how these are related, we can see, in fact, that these are multiplied together. We can multiply our equilibrium expressions to get the equilibrium expression for a combined reaction. Notice that just like before, methane cancels out, 3 of the hydrogens cancel out, and everything else there is just multiplied across. And so, if, let's say our reaction for this one, let's see what our, let's put out some numbers here. Remember, this whole thing, these were just equilibrium expressions, right? So they are numbers. So all we have to do is multiply them together in order to figure out what our new reaction expression is going to be. Equilibrium expression, that is. So if we have 3.97 times 3.3, then the fourth, our new Kc will be 3. Did I say 3.97? 3.92. 3.92 times 3.3 times 10 to the fourth. Doing this, we end up getting looks like 1.29 times 10 to the fifth power, and that would be your equilibrium constant for the combined reaction. So we can kind of, just like with Hess's law where we added the enthalpies together, with equilibrium constants we're going to multiply them together so that the equilibrium expression will work out. Alrighty. So kind of the things that we can do with equilibrium constants, if you reverse your reaction, you will invert your equilibrium constant. So if you just switch your reaction around, you get 1 over Kc. So if you have A plus B going to C, let's say you have your Kc there. If you decide instead you want to write it this way, you get 1 over Kc. So you just invert it if that's what you wanted to do. So much like with Hess's law, you remember, you switch things around, you would make it negative. In this case, you would invert it. So exciting stuff. If you multiply by whatever coefficient you want, let's say it's n, if that is your Kc, if you decide to multiply all of those by some number, whatever it happens to be, you end up getting Kc to the nth power. You would raise it to the nth power. We saw that, I think, last time we did a doubling of the reaction, we saw that we squared our Kc as a result. And now, we see that if we combine reactions, we were able to see that, A plus B goes to C, C plus D goes to E. Overall, we get A plus B plus D goes to E. If this was those two KCs, we're going to see that this is going to be the product of those two reactions. So, or if you really wanted, you could say it's the capital pi. You know, so sigma notation, you add up all the stuff. Pi is the multiplication version of that. So you would just multiply all the steps together, and you'd get that. So you can mess with all this kind of fun stuff. So here, let's do one maybe. Let's do a practice with this so we can see how to kind of come up with new equilibrium constants. So, let's see. Yeah, let's do this. No, let's do CH4 plus O2 turns into CO2 plus H2O. And we're going to say, let's take that water and somehow oxidize it some more. Yeah, let's do it. Two of those, I guess. All right. So if we wanted to have our overall reaction, here, let's put some KCs out here. Just going to make these up. Let's say it's going to be 2.94 times 10 to the 10th. And this will be 1.62 times 10 to the negative 3. I don't know. Making these completely up out of nowhere. But they should make sense, right? Of course, a combustion reaction, we would expect to very, very heavily favor the products over our reactants. Okay, so let's see what the overall reaction is going to be. Let's see what is for I don't know how to add mega. Oh goodness, no 302s. Yeah. Sorry, we're gonna need two of these. No, we're not. Yes, we are. Sorry, I don't know how to do math in my head, guys. I think we already know this by now. Okay. Yeah. Let's do that one. So, hopefully my math is correct here. But let's see what this reaction would be. So, if we wanted to combine these, we could do that, right? However, we are going to not have enough, so we're going to want to multiply this one by 2, so that we will end up with 2 methanes, for example. Notice we would end up with 2 waters as well, because that's what we need to produce or to go forward with our second reaction. And so we're going to need to multiply the first reaction by 2. Second reaction we're going to leave alone. If we do that, we know that the Kc for the combined reaction is going to be the combination, or anytime we're combining things, we're going to have to multiply them together. Since we had to raise or double the first one in order to add these reactions up, we're going to have to square that particular equilibrium constant. If we were to reverse the reaction, we would invert it. Right now we're doubling it, so we have to square our equilibrium constant. And so we're going to see that we're going to need to plug in the numbers. Do this fun stuff, and we would be able to come up with our new one. Thank you. Awesome. seems to be reasonable. Yeah, we are 10 to the 20, but 10 to the 3. Yeah. And that would be our kind of overall equilibrium constant there. As you can see, that one super duper heavily favors the products. It just happens to be the way that I've written this problem, so hooray. So just like with Hess's law, you can manipulate your KCs if you want to. Lots of fun stuff you can do there, I guess, but just another skill you have, perhaps. Alrighty. So nothing new there, perhaps. I guess we've already really talked about all these, except with combining reactions, so just one more thing for you guys. Alrighty. Any questions on that? Alrighty. Then let's talk about kind of our last little bits here. We're going to have an important concept called the Chatelier's principle. French chemist, of course. The TLDR of this is that you mess with equilibrium, not mass your equilibrium. If you mess with an equilibrium, it will try and reestablish itself. That's essentially what we're going to be looking at here. So we're looking at ways to mess with an equilibrium, and we're going to see that it's going to do everything it can to reestablish itself. And so I should really make that not so horrible. So we're going to look at a couple of ways to do that. So let's say we have a reaction at equilibrium. Let's say we have our absolute favorite reaction. We've got our Haber process here. Let's say that we have, I don't know. Let's say this reaction is at equilibrium. It's happy it's at equilibrium. If we start messing with it, we can see how that's going to change Q. And looking at Q, as we saw, was one way to predict what is going to happen next with your reaction. So if let's say we add more ammonia to this vessel. Well, if we do that, if we make it now 1.5, whatever units we're using, atmospheres or molar or whatever they are, we're going to see, as a result, adding more NH3 means we get Q to increase, right? NH3 is a product. It's going to be on the top of our reaction. As a result, if Q increases, then Q is going to be greater than the equilibrium constant. And so the reaction has too many products. And as a result, the reaction proceeds in the reverse. So it's going to take those products and start breaking them down back into reactants. And so we would call this, it shifts left, or shifts to the reactants. So your reaction will shift its kind of current way in order to reestablish the equilibrium. All right, if we were to do the opposite, if we add more reactant, then Q goes down. If Q goes down, then Q is less than Kc. which means too many reactants, of course, which means that the reaction proceeds forward, or we could call that it shifts to the right. It's going to now, currently it's favoring the reactants, but now we're going to make it favor the products instead. It's going to end up making more of those just through reestablishing the equilibrium. Hopefully this is not too crazy. We've already looked at Q and see what happens with that. So basically, everything is nicely in balance here. Here we have our we've got our happy balance. As soon as we add extra of something, it's going to want to reestablish the balance. So if we give it another ammonia, that's going to push our reaction too heavily towards the products. So as a result, the equilibrium is instead going to push the other direction by forcing us to have more reactants instead. So it's going to take that and break it down back into reactants, for example. So the equilibrium is always going to kind of do the opposite of what you do to it in order to reestablish itself, to fix you done did the equilibrium wrong. It's going to remedy that. So there we go. So if you mess with concentrations or pressures of your partial pressures, that is, it's going to reestablish itself by going the opposite direction. So if you give it more reactants, it's going to shift towards the products. If you give it more products, it's going to shift towards the reactants. We're going to see the same thing is going to happen if we do the opposite way. If we remove reactant, let's say we do that, that means we have too many products. Now, products. Or we could say that that's also going to make Q go up. Either way, you want to look at that. If you have too many products, then you are going to goes reverse, or it will shift left. So adding products will shift it left, or removing reactants will shift it left. Either way, you're doing the same thing to it. You're going to make an excess of products. Excess of products means you're going to have to shift your reaction to make more reactants. And guess what? If you remove products, it's the same thing as adding more reactants, so you're going to end up shifting to the right. We're going to see there's two other ways we can mess with equilibriums. One of them is going to be by changing the temperature, and the other is going to be doing a volume change. So let's take a look at what temperature effects are going to happen here. So let's just recall for a sec. If delta H is negative, that's an exothermic reaction, right? Which means that heat is a product. So if you have some reaction that is exothermic, we have a negative delta H here. We can treat heat as a product. And so we can see that if we were to increase the temperature, that means more heat. That means more products. we're going to have too many products. And as a result, the reaction shifts left as a result. So just treat heat as though it were a product or reactant in your reaction. If your reaction is endothermic, you're going to have heat as a reactant. And so if you increase the temperature of an endothermic reaction, you're going to shift it to the right instead. If we decrease the temperature, that means we have less heat for this particular problem. That means we have less product. That means we have too few products. And your reaction shifts right. And notice it's just going to be the opposite for endothermic reaction. For both of these cases. So if you have an exothermic reaction and you cool it down, that's going to help it proceed towards the product side. This doesn't really have anything to do with rates right now, technically speaking. Remember that reaction rates do go up with temperature. That's not something that will ever change. But remember that equilibrium is when your reaction rates are equal. And so since these are reversible reactions, increasing the temperature will just make it kind of go back and forth, more quickly on either side. However, if you're looking at the heat as part of your reaction, cooling it is going to still shift it to the right. So ignoring rates for now, you're going to end up producing more of your product in order to compensate for that loss of heat, which is a different product in your reaction. Alrighty. So questions on that one? Either the concentration or temperature change before we look at volume changes? All right. The volume changes are going to be particular for gaseous reactions, or something that has a gas component. So remember, just throwing it out there again, equilibria kind of don't take into account solids or liquids. We kind of leave those out of our expressions, and so those aren't going to change anything. However, if we have gaseous components and we change the volume of those, we're going to see that can potentially disrupt our equilibrium as well. We're going to see that if we decrease volume, that means we're going to increase the pressure, right? We know that volume and pressure are inversely related. So small volume means more collisions with the wall, more collisions is more pressure, right? We have a bunch of arrows here. We'll just put a then instead. If we increase the pressure, we're going to see that sometimes this has an effect. So if we, for example, take a look at Kp, for example, of some reaction, here, let's say it's our absolute favorite reaction of all time for this chapter. I should just copy paste it, right? Have it just ready to go on my clipboard. If we look at Kp, that's just going to be the pressure of ammonia, pressure of nitrogen, pressure of hydrogen cubed. Since the pressure would go up by the same amount for each gas, so let's say if we our volume was 1 or something. We made it now half of a liter. If we halve the volume, we double the pressure. If we double the pressure, that's going to double the partial pressure of all of these components. As a result, let's say we do that. Let's say if we double the pressure, we have to take into consideration these exponents. So that means we have 2 times the partial pressure for ammonia. And so if we square that, that now becomes 4 times our pressure squared. And if we just follow through with the rest of it, we're going to have 9 times... Wait, what are we doubling? So it's actually 8. And as you can see, if we we'll take a look at substituting the rest of our regular Kp in there, we see that in this case, this is just half of our original Kp. Kp had those cubes and squares already. We basically now have 4 over 8. Notice we have half of our equilibrium constant right now. And remember, equilibrium constant does not change unless you're changing the temperature. So, as a result, this means that this part here is really a Q. If Q is 1/2 Kp, Q is going to be too small, right? And as a result, Q being too small means we have too many of our reactants, and so we're going to go towards the product side. That's a lot of words, but there's an easy way to do this. If we increase the pressure, we're going to see that the easiest way to look at this, if P goes up, the reaction will shift to the lower moles of gas. That's always going to be the case if you increase pressure. In this case, we have 4 moles on our reactant side, and we have 2 moles on our product side. So if we increase the pressure, the equilibrium is going to shift to the side with lower number of gas moles. So that's going to end up shifting to the product side in this reaction. We're going to see that the reaction will shift to the right, and it will make more ammonia as a result in order to fix this problem. So you can also think of it in terms of concentration. We're decreasing our volume. That's going to increase the concentration. So it's going to be working exactly the same way, looking at it in terms of concentration instead. This is not really a concern for aqueous things because it's very hard to change the volume of that. Unless you boil some water away or something, it's not really kind of sensical. Whereas gases, we can change the pressure, no problem. We're going to see that a decrease in pressure is going to be the exact opposite. So you can work through it mathematically if you want. You're going to see if we were to double the volume, we would have the pressure. We would end up with 2 times Kp as our Q. And so we're going to see Q is too big, and therefore Q is going to end up having our reaction shift to the left instead. So if you decrease the pressure, the reaction will shift to make more moles of gas. And in this case, that would end up making more of our reactants if we were to decrease the pressure by increasing the volume. So there's a lot of if this, then this, then this, then this going on with this principle, but it's really, it all goes down to, messing with equilibrium. Take a look at what that's going to do for your Q. And as a result, once you have your Q, you can evaluate it compared to regular equilibrium constant and see which way things are going to flow. But by and large, it's going to do the opposite of what you have done to it. So it's going to try and reestablish what it used to be, kind of at all times. So let's see, 11:11. We were pretty much out of time today. So tomorrow we'll just kind of go over some general problems. I'll come up with a couple. Maybe we'll take the full hour, maybe we won't. We'll see how many problems I can come up with and how quickly we go through those. I'll put up your homework tonight. It's going to be a little bit shorter because this has been a pretty short chapter. It'll be due Saturday as well. So you will have 2 homework assignments due Saturday. Hopefully you have been working on the kinetics one. I'll also see if I can scrounge up a practice exam for you guys, so you can take a look at that. And then Wednesday we'll go over any sort of, we'll just do a review on Wednesday. So whatever you guys want to do, we'll, ask questions and do that sort of thing. And then you'll have your exam next week. So your exam will be on these 3 chapters, so solutions, kinetics, and our first equilibrium chapter. After this, we have kind of more equilibrium fun. We're going to talk about acid-base equilibrium and then other equilibria. I think it's pretty funny. The most textbooks just say like additional aspects of equilibria, and it's like, I don't know why they decided to separate into another chapter, but whatever. So yeah, it's going to be exciting. So with that, I guess I'll see you guys tomorrow. Keep working on your homeworks. And yeah, awesome. See you then.